morning. Good morning to everyone. Yes, good morning. So, before starting with the class, I will inform that even you can tell to your friends also. So at 10:30 there will be physics class. There will be no math class today. Okay? So directly it will be at 10:30. We will be having physics class. So all of you are listening, right? So there will not be any math class today. So directly at 10:30 you will be having physics class. So please inform to your friends also who have still not joined this particular class. You can inform them also. Anyway, so before going to today's concept, as usual, I will be briefly talking about whatever we have discussed in the last class. Okay? So that is D and F block elements. Right? Now when it comes to D and F block element, in the last class we have discussed about redox couple, formation of the redox couple, where it will be M plus 2 and M, where redox couple will be having ionic form, which will be having plus 2 charge. Then we have discussed about M plus 3, M plus 2, that means continuation of this. Right? Now when I am talking about M plus 2, so we are going to deal with the ionization potential and ionization potential 2. That means ionization energy. Energy required to remove the electron. So when we are talking about this one, we are dealing with ionization energy 3. So that's what in the last class we were talking about. Which particular element is going to donate the 2 electrons easily? Which is that particular element which can donate the 3rd electron also easily? That's what we used to discuss. We have discussed. So when it comes to here, it is manganese and zinc. They are going to dominate. They are going to donate the electrons easily. Right? So that's where we have the manganese and zinc. Why they are going to have the very low value here, standard redox potential value? Why I am telling low value? Because they will be having negative sign. So which will be having highest negative value? So these two are the one which will going to dominate, because they will attain the stability. Now when it comes to here, scandium is one of the element which is going to dominate with respect to negative value I am talking about. Why scandium? Because it will attain the electronic configuration of inert gas. Right? So therefore scandium is going to have the high negative value when it comes to this particular redox potential condition for formation of this particular redox couple. All of you will agree? So that's what we have discussed in the last class. And one of the exceptional cases is ferric, Fe plus 3. That's where we have the some of the exceptional case. So what I mean to tell here is, in some of the case, electronic configuration, stable electronic configuration, based on that only we can tell that whether they are going to donate the electron easily or not. But in some cases it will be other factors which is going to count, like atomization enthalpy or sublimation enthalpy. Then we have the ionization enthalpy, and finally we have the hydration enthalpy. So these are the 3 factors which are going to count, or which is going to decide SRP, that is standard redox potential for a particular element. All of you have understood? So that's what we have discussed in the last class. And someone had written magnetic moment. Someone had written, that is Suresha. Yes, we have discussed about magnetic moment, which is very important for your exam point of view. Where when it comes to magnetic moment, that means related to magnetic property, where nu is equal to square root of n into n plus 2 Bohr magneton. Whatever answer comes, it should have the unit Bohr magneton. That's where we have the equation. And by using this equation, we can calculate magnetic moment for any of the element. So that's where nu stands for magnetic moment. And n stands for number of unpaired electrons, not the number of electrons. Unpaired electrons. Some students, they will write in a hurry. They will write n as number of electrons. No, it should be very specific. Number of unpaired electron, right? So that's where we have the equation. So by using this equation, we can calculate magnetic moment for any of the element, whether it is an ionic form or whether it is an atom. We can calculate. But what is basically required here? You should know the electronic configuration. So if you know the electronic configuration, then only you will come to know what is that number of unpaired electron. So based on that, you can calculate. All of you will agree? And manganese is the one which is going to dominate with respect to highest oxidation number, that is oxidation number. When it comes to magnetic moment, manganese iron is the one which can have the highest property, magnetic property, that is paramagnetic property, right? So now when it comes to diamagnetic element, if I focus on 3D series element, if that is the case, diamagnetic property will be shown by zinc and its ion, that is zinc plus 2. In both the cases, it will be diamagnetic because the magnetic moment will become 0 for these two forms. Okay, so that's where we have the diamagnetic element. If I take paramagnetic, then we can have the chromium, manganese. Okay, so these are the some of the example. Almost all the element except iron, cobalt and nickel. Almost all the element, they can be considered as paramagnetic. Even Mn plus 2, chromium plus 3 ionic forms, they are all having paramagnetic property. Then we have the ferromagnetic property or ferromagnetism showing element. So ferromagnetic element. So which are those? That is iron, cobalt and nickel. Iron, cobalt and nickel. They are the ferromagnetic elements. So why they are called as ferromagnetic? Because if you provide the condition, they can be converted into a magnet. Because they have strong affinity towards, or they have the strong magnetic field, magnetic moment. That's where we have the ferromagnetic substance. Okay, so that's what we have discussed in the last class. So along with that, we have discussed about Curie point. Anyway, these things you people have discussed in your physics. That means at one particular temperature, that is Curie point, at one particular temperature, a ferromagnetic substance can behave as a paramagnetic substance, or a ferromagnetic substance will be becoming paramagnetic substance at that particular temperature. That's where we have the iron at 768 degrees Celsius. It will behave as a paramagnetic substance. All of you will agree? So that's what we have discussed in the last class. Okay? So now we will move to the next one. All of you have discussed about coordination compound. All of you have discussed about the coordination compounds. Now if you observe these particular compounds, definitely there will be presence of a metal and there will be presence of a non-metal. So together they are going to form the coordination compound, where we will be having elements inside the square bracket, group of element, and outside there will be another element which will be acting as a counter ion to neutralize the charge on this square bracket, right? So that's where we have the coordination compound. Now if you observe it carefully, here we can have the metal and here also we can have the metal, no doubt. We can have the metals. In most of the coordination compound, inside the square bracket, it will be transition elements or transition metals. Why I am telling most of the compound means sometimes some of the metal can be alkali or alkaline earth metals, but that is very less. We can have the transition metals which will be present inside the square bracket. And all the coordination compound, transition metals are the one which will be interacting with the ligands. I am not going to explain in detail because already this chapter has been done. So in all the coordination compound, transition metal is the one which is going to interact with the ligands, which is going to make the coordinate bond with the ligands, right? So now outside it can be any metal, even it can be sodium, potassium, whatever, they can be present outside. So what I mean to tell here is coordination compounds are those where transition metal should be there or it will be there. That's a must. So that shows the efficiency of transition metals in forming the coordination compound. All of you will agree? For example, we have potassium ferricyanide, potassium ferrocyanide, like this list will go on. Cupramonium sulfate, right? So if I take this whatever example where iron I have in different oxidation state or ionic condition, in potassium ferrocyanide it will be +2, in potassium ferricyanide it will be +3, right? So that's where we have the compound. And if you observe these elements, so that's where we have the potassium which is present. I am just representing. That's where we have the potassium outside. Coordination compound, that is transition metal, inside. That's what I told in the beginning. Outside it can be alkali metal or alkaline earth metal, but transition metal is the one which is going to make the coordinate bond with the respective ligands. All of you will agree? Now, question here is, sir, when I am talking about alkali metals or alkaline earth metals, when it comes to reactivity and all, they are reactive element because they are very good donors of electron, right? During the salt formation, alkali metals, they are going to dominate. Then what is the reason why coordination compound, they are going to dominate when it comes to formation of coordination compound? Why it is transition metals, they are going to dominate? Why not alkali or alkaline earth metals? That should be the question, right? Now, the answer for this one is very simple. When I am talking about periodic table, I have the element which is on the left side, and when I am moving towards the rightward direction, what is happening? Atomic size is going to decrease. Now, it's very easy, or we can easily tell that, yes, of course, if I compare the atomic size of alkali metals with 3D series element or transition element, any other transition element, definitely we can tell that alkali metals will be having larger size compared to the transition element or 3D series element. Right? All of you will agree with that, because alkali metals, they are present on the extreme left of the periodic table, and when you are moving rightward, That's where we are going to get the transition metals. So that means atomic size has to decrease. Atomic size of transition element should be less compared to alkali metals. Fine? That is one answer. That is one point you should remember. Next one is, when I am talking about alkali metals, they will carry single positive charge. They will carry single positive charge. We don't have a compound where potassium will be +2. No chance. We don't have a compound where sodium will be +3. No chance at all. It's not at all possible. Alkali metals, always it will have the one or single positive charge. If I take alkaline earth metals, they will have maximum +2 charge. We don't have a calcium which can carry +3 charge. No, it does not exist in the nature. Right? So what I mean to tell here is, when I am talking about alkali or alkaline earth metals, their valence is constant. There is no variation. So they are having valence as +1 or +2. But when it comes to transition metals, it is variable. They can have the multiple positive charge. Right? So ferric, ferrous, cupric, if you press, so like that, chromium, cobalt, all of them, they can have the multiple positive charge. Right? So what I mean to tell you is, when it comes to alkali metals or alkaline earth metals, amount of charge is constant and it is restricted to 1 and 2 respectively. But when it comes to transition element, they can have the multiple positive charge. They can have the multiple positive charge. All of you will agree? So that's where, when it comes to atomic size, alkali metal and alkaline earth metals, they are going to dominate. When it comes to the charge, now transition elements, they are going to dominate. All of you are agree? Okay. So that's where we have one of the equation. That's where we have the equation. That's with respect to one of the term, which is called as polarizing power. Polarizing power. Okay. So which is equal to charge by size ratio. Somewhere you people have discussed this in first PU. Somewhere.
Charge by radius used.
Okay. Charge by radius or charge by size is one and all same, na? Radius talks about size only. Charge by radius somewhere, that is related to anomalous property of first element of that particular group, and it with respect to Fajan's rule. That's where we have discussed these things in chemical bonding, right? So that's where we have the polarizing power. Now, can any one of you tell me, if I want to compare between a transition metals and other metals like group 1 and group 2 metals, which is going to have the larger value in polarizing power? Any one of you? Which can have the larger value? Definitely, when I was talking about the charge, transition metals, they are having the higher charges. Transition elements, right? They are having higher charge compared to alkali or alkaline earth metals. When it comes to size, group 1 and group 2, they are going to dominate. Group 1 and group 2, they are going to dominate. That means, what I mean to tell here is, when it comes to transition metals, they will have the larger value with respect to the charge. And when it comes to size, alkali or alkaline earth metals, they will be having larger value. So that means, in the denominator, alkali or alkaline earth metals are dominating. In the numerator, transition metals are dominating naturally. Since numerator transition metals are dominating, polarizing power is high with respect to transition elements. It is higher with respect to transition elements. So therefore it can have efficient interaction with multiple ligands. Due to the higher polarizing power, it can have efficient interaction with the multiple ligands. Because in the ligands we have the neutral, negatively charged and positively charged ligands. Right? So that's where we have the ligands. So with respect to negative and neutral ligands, with respect to those ligands, transition elements can easily interact due to high polarizing power. That is one reason why coordination compounds are dominated by the transition elements or transition metals. All of you will agree? Fine. So this one you have understood. Any doubt in this? Now we will come to second one. Another important reason. So another important reason is due to the availability of empty d subshell. Due to the availability of empty d subshell which is there with respect to transition elements. Due to the availability of empty d subshell where these ligands can fill their electrons to form the coordinate bonds. So therefore, due to the availability of the empty d subshell in transition element, once again they are going to dominate with respect to formation of coordination compound. All of you have understood? So these two are the major points why coordination compounds are dominated by the transition elements. Any doubts? All of you have understood? If you have any doubts, you can ask. Okay? Now, another important point here is when it comes to coordination compound, as there is an increasing in the atomic number of transition elements, as there is a increase in the atomic number of transition elements, I am talking about properties which is going to decide, property of transition element which is going to decide the stability of a coordination compound. About that I am going to tell now. So when it comes to transition element, as there is an increase in the atomic number, stability of atomic number of what? Atomic number of transition metals, TM. Don't use the short form. Okay, I have written to save the time. So to increasing in the atomic number of transition metal will lead to increase in the stability. Increase in the stability. That is important point. It's going to lead to increase in the stabilities. Therefore, most of the coordination compound will be having iron, cobalt, like that, right? Copper. So we will see very less with respect to manganese and scandium, right? So that's where as there is increasing in the atomic number, there will be increase in the stability. Fine? That is one thing. And another reason, since there is increase in the atomic number along the period, there will be decrease in the atomic size also. So they can easily accept the electrons to make a coordinate bond. So that is the reason why, since there is increasing in the atomic number, why there should be increase in the stability of the coordination compound. That is one point. All of you have understood? Next point here is, as there is an increase in the oxidation state, as there is a increase in the oxidation state of transition metals. It will lead to increase in the stability of coordination compound. As there is an increasing in the atomic number, it's going to increase the stability. As there is an increase in the oxidation state, it's going to increase the stability. So because of that, we can tell that potassium ferrocyanide and potassium ferricyanide, which has to be stable, potassium ferricyanide has to be bit stable compared to ferrocyanide. Why? In ferricyanide ion with +3 and in ferrocyanide ion is with +2. So therefore, that's where this particular statement is applicable. All of you have understood? Any doubt? So shall we move to the next part? Fine. So what I have written 2 points here, it is related to it is related to part of transition metal, role of transition metal with respect to stability of the coordination compound. That's what these 2 points talks about. Okay? So we will move to the next part, that is catalytic properties of transition metals. Next here is catalytic property. Catalytic properties of the transition metals or catalytic role of transition metals in different reactions. Can any one of you tell me any one reaction name? That's all. Many reactions we have discussed. Wow. If I tell, you will feel very bad. That is Haber's process. Simple example is Haber's process, where nitrogen, hydrogen in the presence of iron powder, it will get converted into ammonia, right? So that's where we have the Haber's process. What is iron? Iron belongs to transition metals. Iron is a transition metal. Same way, conversion of SO2 to SO3. Which transition element they will use? In which particular this one we have discussed this reaction? Where? Wow, P block element completely woodies. We have discussed this one in contact process, preparation of sulfuric acid, right? So that's where we have the platinum based catalyst which will be used, right? Same way, if you go with high school, since from high school you are studying hydrogenation process. We are talking about hydrogenation process. What is hydrogenation? That is addition of hydrogen, right? So that is conversion of unsaturated fatty acid containing oil into saturated one. Where it will happen? It will happen with respect to preparation of vanaspati, dalda, which people will be using, right? Not at home, outside in the hotel and all. At home, no mother will prefer vanaspati because it's not good for health, right? So that's where hydrogenation, where palladium or nickel catalyst they will use. So what I mean to tell you is these are some of the example. Even in Ostwald's process, they will be using the transition element, contact process, Haber's process, hydrogenation process. There are plenty of reactions where metals will be used as a catalyst and that metal will be transition elements. Now, what is the reason? Why or on what basis transition metals they can use as a catalyst compared to alkali and alkaline earth metals? What might be the reason? The reason here is very simple. when it comes to alkali or alkaline earth metals, as I told, they will have +1 or +2 charge respectively. Alkali or alkaline earth metals. But when it comes to transition element, they can have the multiple oxidation state. They can have the multiple oxidation states. That's where they are going to dominate as a catalyst. They are going to dominate as a catalyst. That is one of the important reasons. Right? So that's where. What is the advantage, sir? What will happen? Now they will be involved in some of the reaction in such a way that they will form an intermediate and there will be reformation of the catalyst. That's where multiple oxidation state is going to helpful. That is happening with respect to transition metals. That is one thing. Now, as a powder form, these are the metals which will provide large surface area, which we have discussed with respect to this point. We have discussed with respect to surface chemistry. Very good. So, powder form, it will provide large surface area. Alkali or alkaline earth metals, especially alkali metals, they are soft, right? So therefore, powder form of these transition metals will be helpful in for providing the large surface area. Fine? Any doubts? So these are the two major reasons why transition metals can act as a catalyst, unlike any other alkali or alkaline earth metals. All of you have understood? Any doubts in this? So these are the two major points which you have to remember. Okay? Next one is interstitial compounds. This is bit important. Okay? So that is related to interstitial compounds. Okay? Now, before going for the detailed explanation, you should tell me what you mean by interstitial.
Space between.
Okay, this one we have discussed in the crystal defects, right? So interstitial defect, right? So that's where we will be having a structure, solid structure, where we will be having a regular element which belongs to that particular solid structure, but in between there can be any other element which will be of smaller size. So this condition is called as interstitial, right? So this condition is called as interstitial, where between the element there will be presence of another element. Naturally this can happen when we have the large sized element in combination with the small sized element. All of you will agree? It's not possible if you have two large elements. It's not possible. It should be large elements in combination with the small elements. Fine? All of you have understood? So that's where we have the interstitial compound. Now when it comes to interstitial compound, with respect to transition element, that small element can be hydrogen, carbon, etc. Normally it will be hydrogen and carbon. In some extent it can be one boron also. So hydrogen, carbon, boron. So these are some of the elements which will be used for the preparation of interstitial compounds. So in turn we can define that interstitial compounds are those where transition elements are in combination with smaller elements like hydrogen, carbon or boron. Fine? So therefore it can lead to hydrides, right? If it is in combination with hydrogen, it can lead to carbides. If it is in combination with carbon, or it can lead to borides. If it is in combination with boron. All of you got my point? So hydrogen, if it is the interstitial compound where transition element, it can be any of these, platinum, cobalt or whatever it is. So if they are in combination with hydrogen, then it will become respective hydrides. If they are in combination with carbon, it can be carbides. If it is in combination with boron, then it will be borides. Fine? So that's where we have the compound, interstitial compound. Now the point here is they are having non-stoichiometric. They are having non-stoichiometric combination of these transition elements with the hydrogen, carbon or boron. Non-stoichiometric combination. What do you mean by non-stoichiometric? That means we cannot have exact ratio. For example, if I tell H2O, now I can tell that 2 of hydrogen, 1 of oxygen. The ratio of hydrogen to oxygen here is 2:1. So that cannot be defined when it comes to interstitial compounds. So therefore it is called as non-stoichiometric. Okay? So sometimes or in some of the cases we can define cobalt boride. They will write it as cobalt boride as CO3b. So they will call it as cobalt boride as CO3b. Now the point here is it is not exactly same as that of their molecular formula. That is because when I am talking about this interstitial compound, these elements, hydrogen or carbon or boron, they are not making any bonding with the transition elements. They are just present in between the space. Got my point? So that is the major point here. Once again I will tell, when it comes to interstitial compound, they have the non-stoichiometric relation between transition element and the small element which are present. Now, why non-stoichiometric? That is because these elements, that is hydrogen or carbon or boron, which are common one, they will not have any interaction with the transition metal. They will not make any bond. They have occupied that particular space in between the transition metals in their solids. Fine? So therefore they are non-stoichiometric in nature. Interstitial compounds. All of you have understood? Now, speciality of interstitial compound here is they will be much more stronger. They will be much more hard. Okay? So compared to transition metals, I am talking about, interstitial compound will be more harder and will have higher tensile strength. They will have higher tensile strength. So that's where we have the interstitial compound. They will be much more harder. They will be having higher tensile strength. That means they should have higher melting point. They should be having higher melting point. Okay? So for example, we have titanium boride. We have titanium boride. Okay? So this is almost hard as that of the diamond. It's almost hard as that of the diamond. That's where we have the titanium boride or interstitial compound. Right? But at the same time, they have the regular property of the metals, that is malleability and ductility. Even they have the luster, that is the property of the metals, luster. So they have the metallic luster. Even compared to malleability and ductility, we can tell conductivity. lustrous and conductivity. All these properties are present. There is no change with respect to these properties which are present in the transition elements. Okay, that's where we have the property. Interstitial compound. Fine. So due to that particular properties where higher melting point, more harder and higher tensile strength and all, they have the huge application also. They have the huge application. For example, when I am talking about application, hydrides. When I am talking about hydrides, they will be used as a semiconductors. They can be used as a semiconductors. Okay, na? Or they can be used as a reducing agent. They can be used as a reducing agent. That is one point. That is one point. Now, can any one of you tell me where boroids will have the application? They are the hardest material. Where boroids will be having the application? Anyone?
Cutting or shaping instrument.
Yes, very good. So naturally it will be used in the turbine blades. Which will be used in the turbine blades. Even in rockets. Okay. So these are some of the application of the boroids. These are some of the application of the boroids. Same way when it comes to carbides. They will be used in cutting tools. They will be used in the cutting tools. They will be used in the cutting tools. Okay, these are some of the application. Like tungsten carbide and all, they will be used in the cutting tools. So these are some of the application of the interstitial compound. So what do you mean by interstitial compound? So these are the compound which are resulted due to combination of transition metals with smaller elements like hydrogen, carbon, boron, etc. Fine. Now if it is the combination with hydrogen, then it is called as hydrides. If it is in the combination with carbon, it is called as carbides. And if it is in combination with boron, it will be boroids. That is because hydrogen, carbon or boron will have the negative oxidation state. Therefore, they are called as hydrides, boroids and carbides. Okay. Now, what is the speciality of interstitial compound? They will be much more harder and higher tensile strength compared to transition metals. Now, they will be having higher melting point. So, they will be having conductivity which will be not affected. Lustrous which will not be affected. Okay. So, due to that property, they will be having huge applications like hydrides will be used as a semiconductors or reducing agent in some of the reactions, and turbine blades and all or rocket nozzles, all these things will be prepared by some of the boroids, and cutting tools, it will be normally prepared by the carbides. Tungsten carbide and all will be utilized for the cutting tools. Fine. So this is with related to interstitial compound. Any doubts? So this is bit important, interstitial compounds. Any doubt is there? Okay. So in that case, we will move to the, okay, alloy is there. Alloy people have studied in any other topic, solution or any. So next one is
Get into solutions.
alloys. Okay?
We haven't done solution.
Okay, then fine. Then alloys. We are going to discuss about the alloys. Most of the alloys, they are having one of the common element as transition metals. They are having common element as transition metals. Please remember. Now alloy is nothing but a combination of metal with another metal in a particular ratio. Alloys are nothing but a mixture. Better word is mixture of. It is a mixture of. It is a mixture of metal with another metal in a ratio, in a specific ratio. Okay, na? Other elements can also be present, non-metals, but it should be metal with another metal. That's where it differs from the interstitial compound. In interstitial compound, hydrogen, carbon and boron and all, they are non-metals. So transition elements are in combination with the non-metals in a non-stoichiometric way. But here it will be mixture of metal with another metal. That is the difference with respect to alloy and interstitial compound. Fine. So now one of the example for this is very commonly used one is stainless steel. Okay. So can any one of you tell me what is the combination? Which are those metals which are present?
Iron, chromium, cobalt, and
Okay, normally stainless steel will be iron and chromium. I am not giving the percentage, I have forgotten. Okay, na? So iron and chromium, these two are the transition metals, and to some extent they are in combination with carbon and even with nickel. Carbon and nickel. So carbon is a non-metal. Anyway, nickel is one other transition element. But major portion will be taken care by iron and chromium. Okay, major portion will be taken care. Even nickel will be there. But iron is carbon is a small proportion which will be present. Okay, so that's where we have the stainless steel. If you go with chromium steel, we have another steel which will be used in armor preparation to provide the hard material, that is armor preparation and all. We have chromium steel. It will be used in stainless steel, all of you know, utensil preparation. Then we have the chromium steel which will be used for the armor preparation. So where iron and chromium will be the one, nickel will not be there. Iron and chromium, and to some extent it will be in combination with the carbon. So that's where we have the chromium steel. So if I see here, iron and chromium we have in these two alloys, right? But same way we have bronze. Same way we have the bronze. Can any one of you tell me bronze is made up of? So it will be copper and tin. It will be copper and tin which are in the combination. Small amount of other elements can be included, okay, but these two are the major proportion, copper and tin. Same way we have the brass.
copper and zinc.
Yes, it will be copper and zinc. So what I mean to tell here is, in case of the alloys, major proportion will be taken care by two different transition elements, two or more transition elements which are in the combination. That's what we can see when it comes to the alloys. Then what is the difference between alloys and interstitial compound? In case of the interstitial compound, it will be a non-metal, small element which are present along with the metals. But here It is metal with metal. Even gold can be an example for alloy, where gold is mixed with small amount of copper. So then only we can have the hardness in the gold. Otherwise it will be a soft metal. Making design will be difficult. Okay? So that's where we have the alloys. All of you have understood? Any doubts up to here? So next one we are going to discuss here is very important one. So that is compounds of transition element, especially we are going to focus on potassium dichromate and potassium permanganate. Okay? Now, even now PU board has not officially released which topics has to be removed, but in some cases there are some WhatsApp group is there, na? They will be sending some forward message where this particular topic they have removed. They are telling, we don't know. But whether it is official one, it's not sure, because whatever I am discussing now, that is very, very important for your exam point of view. Very often they have asked the question on this concept in the board exam. But according to that particular table, this topic itself is not there. So how much true, we don't know. But until now, according to this one, it's not have been given officially. Which topic is not there in chemistry. Especially this particular topic is not there. No one has told officially. So what I will do is, we will discuss about all these things. If it is not there, once officially it is declared, we will remove those things, but it will be helpful for your competitive exams. Maybe for board exam they might be removing, but for competitive exams it will be there. Okay? So first we are going to discuss about preparation of potassium dichromate. Anyway, preparation we are not going to discuss today. I will give a brief introduction. Okay? Now, when it comes to potassium dichromate, which type of compound it is? Formula we know, K2Cr2O7. Which type of compound? No, it's not a coordination compound. That is because there is a presence of covalent bond between chromium and oxygen. Okay? And please, one thing, okay, here I remember. Chromium can go up to +6 here. Right? Please remember, as I told, manganese, same logic is applicable. All these transition elements will have the maximum oxidation number. Maximum oxidation state with oxygen. Not with fluorine and all. They will have the maximum oxidation state with the oxygen. Say for example, permanganate, potassium permanganate, where manganese will have +7. But the same manganese with fluorine maximum oxidation is +4. That is manganese tetrafluoride, MnF4. But with oxygen it can go up to +7. Same logic is applicable here also. So with oxygen they have the highest oxidation state, that is because of the ability of the oxygen to make more than one bond. They can make the double bonds and all, right? So due to that they will have the higher oxidation state. Fine? So that's why we have the potassium dichromate. It is a very strong oxidizing agent. It is a strong oxidizing agent. Even in organic chemistry we have discussed same thing, right? So potassium dichromate is a strong oxidizing agent. So therefore it will be used as a reagent wherever oxidation is required in a reaction. So that's where we have the application of the potassium dichromate. Due to this application, due to its utilization in many of the reactions as a catalyst, as an oxidizing agent, it will be prepared commercial. Okay. So anyway, preparation of potassium dichromate, we are going to have it in the next class, that is tomorrow. Fine. Any doubts? So we have discussed about interstitial compound. Then we have discussed why D and D block elements or transition element they can form coordination compound. Then we have discussed about alloys. So these are some of the points which we have discussed in today's topic. Fine. So tomorrow we are going to continue with a very important one, that is preparation of potassium dichromate and permanganate. Any doubts in today's topic? Okay. So once again I will repeat, in the beginning also I told, we will not be having math class today. So directly you can have the physics class at 10:30. Physics class will be there. Fine. In that case I will stop here. Take care. Thank you. Whether they are responding?